Welcome to this video on questions from group theory, which are asked for IIT JAM 2020. So we have tried solutions of all the problems in this particular video. Please see the video completely to have a look at all the problems which are asked. So the first question is, we are asked to actually find the center of the group of a particular group given to you, and we are asked to check whether it's isomorphic to some particular structure are given out there. So you can see here we are given a group which is under multiplication of matrices, 3 by 3 matrices, something like upper triangular matrices, and all diagonal entries are 1. So this group is nothing but the Heisenberg group, which you might be familiar with. So in this problem, first what I'm going to do is I'm going to find the center of the group, and I'll give you a technique in which using first isomorphism theorem of group theory, I'll try to prove the isomorphism to some structure out there. So as I told you, we'll try to first find the center of the group here. So I'm trying to find all the elements in this group which commute with every other element of this form 1pq 01 r001 in this particular group. So if I want to say that this particular matrix belongs to the center of the group, then this matrix, when I multiply with a particular matrix, I should get it of this form. That is, this matrix should commute with every other matrix in this particular group. So if I take this matrix and if I multiply like this, you can see if I multiply this the first row with the second column here, I'll get what? 1 into p plus a times 1. And if I compare to the element on the right hand side of this equality, here will be what? The first row into the second column. If I multiply, what I get 1 times a plus p times 1. So in this manner, if I finish all the operations here and compare the elements, I'm going to get few implications from that. The first one is just what I told now. I'll get p plus a is equal to a plus b. Obviously it is true, because we are taking here the elements p, q, r all from R. So p plus a is equal to a plus b. There's nothing new in that. Then similarly, I'll get other set is r plus c is equal to c plus r. And the third set of equation, what I get is something but q plus ar plus b will be equal to b plus pc plus q. And from this I will get an implication that ar is equal to pc. That means if this matrix belongs to the center of the group, if I want to check, what I will do, I should multiply this matrix with every other matrix in this particular group and check whether it commutes with that in both ways. Right? I should multiply in both the ways like this. So if you want a matrix like this to commute with this matrix, you must have a condition that what? AR is equal to PC. Similarly, if you want this matrix to commute with, say, some other matrix, say of this form in the group, the condition you are going to get is nothing but AR1 is equal to P1C. Again, if you want to check with another group element of this form, we will get AR2 is equal to P2C, and so on. The matrix, if it is belonging to center of G, it should satisfy something like this. ARI will be equal to PIC, where RI and PI vary completely in R. Because we don't have any restriction here, you can see we don't have any restriction given there in the problem. It's just given P, Q, R belongs to R. So this P and R are basically belong to R. So this is the condition we are getting. So if you want this matrix to be in the center of the group, this condition should be satisfied. So you can just think that if you vary completely Ri and Pi and you go on finding matrices of this form and you check whether this matrix commutes with that, then you have to check all these conditions. So what will be the values of A and C which satisfy this condition? Because we are going to vary Ri and Pi throughout in R. So if you want this condition should be satisfied, the only possibility is that your A and C should be 0. Otherwise, you cannot satisfy this condition for every Ri and Pi in R. So what we get basically is from this that A and B both should be 0. Sorry, not A and B, it should be A and C, both should be 0. It's a typo. And center of group we'll get as what? We'll get elements of this form. That is set of 3 by 3 matrices. You can see with all diagonal entries are 1, and the element A13 is Q and remaining all elements are zeros. Such elements are there in the center of the group H. So now we are trying to address the problem of isomorphism. If you see that but the claim what I'm going to make is that the center of the group is actually isomorphic to the structure R plus. It's actually option B. So what I'm going to do is I'm trying to give you a homomorphism from Z of H to R plus, and I'll later show that it is actually an isomorphism, and then I'll finish the problem. So here we'll define the function as phi of this group element, say element in set of H, to be simply B. That is, whatever is coming in the A13th position, the same element I'm going to give as its image. So clearly you can see it's actually an homomorphism, because if you just see phi of A star B is equal to phi of A plus phi of B. So here just the star is nothing but, in Z of H the operation is nothing but multiplication. So when you multiply you get this matrix, and you find the image of that, you'll get B1 plus B2. It's a typo actually, it's not star here, and in fact B1 is nothing but phi of this matrix and B2 is nothing but phi of this matrix. So what you get is nothing but, it's actually an homomorphism. So clearly it's a group homomorphism from Z of H to R plus. So now if you want to show this is actually an isomorphism, it is enough to show that kernel of phi is what? Identity, set containing the identity in Z of H. So the identity in Z of H is nothing but what? Yeah, it is the element, the identity matrix, 3 by 3 matrix, identity matrix. So here you can see the kernel of the homomorphism is nothing but set containing the identity matrix. Why is it? Because if you see the mapping here, kernel of a particular mapping is nothing but the set of all elements in this domain which are mapped onto the identity element in this group. So the identity element in this group is basically 0, because R plus with respect to plus, so set of real numbers with the operation addition. So here the identity is actually 0, and if you want an element to be mapped onto 0, then this your domain should be actually containing here also 0. So the element, and if you take there is no other element actually which will be mapped on to 0 element under this homomorphism. So what you can say is that kernel of this mapping phi is actually the identity matrix, 3 by 3 identity matrix, because there is only matrix which is mapped on to the identity element in R plus. So what you get is our kernel of phi is actually an singleton set containing the identity element. So our mapping is an isomorphism. So if we use the first isomorphism theorem, what we have is if it is actually an homomorphism, we have what? The result is nothing but Z of H by kernel of Z of H will be actually isomorphic to the image of Z of H. So in this case kernel of phi is nothing but the identity set containing identity alone. So you get Z of H is actually isomorphic to R plus, or it's enough like what we already shown that kernel of phi is identity. So this is actually a isomorphism. So that is a first question, and the answer for that question is actually option B. The only correct option is actually B. So now we'll go to the next problem. Here we are given a group S1, the set of all complex numbers having modulus 1. We can think of all complex numbers lying on a circle of radius 1 in a complex plane centered at 0, 0. So all the points that will be in this particular group, basically known as a circle group under multiplication. So this group is basically known as a circle group under multiplication, and we are asked that the set of all theta in R such that the cyclic group generated by elements of this form is infinite. So we have to find all theta for which cyclic group generated by e raised to I 2 pi theta is actually infinite. and we have to talk about that particular group, whether it is empty, non-empty, and finite, or countable, infinite, or uncountable. So here you can see that is, if you are going to find cyclic group generated by this particular element, what you get to get is e raised to I 2 pi theta, e raised to I 4 pi theta, and so on. We know that e raised to I 2 pi theta, sorry, e raised to I theta is basically cos theta plus I sin theta. It is not I 2 pi theta, it is e raised to I theta, so it is cos theta plus I sin theta. If you assume z to be in its polar form, then mod z is equal to 1, where z is not equal to 0, if and only if r is 1 and theta should be 2 pi k, where k is actually an integer. So this is the only case where you're going to get the modulus of z to be 1. That is, you have the element, the complex number lying on that circle with radius 1, centered at 0, 0. If you fix some irrational number omega in the place of theta over here, if you want this particular set to be finite, like this, the cyclic group generated by this particular element is actually finite, you must have something like, after some time you must have like some e raised to I 2 pi k omega should be equal to 1, right, the identity in this group. So but that is actually not possible. Z equal to r e raised to I theta, where mod z is equal to 1, then what you must have is basically this quantity 2 pi k omega. This quantity should be of the form some 2 pi k, right, where k belongs to z. So 2 into pi, and we have k omega, and that you cannot attain it to be an again integer, which is omega to be something like an irrational number. So you cannot attain this property in this set if you choose your theta to be an irrational number. Okay, so what you get is since we have infinite number of irrational numbers out there in this set of real numbers, set of all theta for which it happens is basically uncountable, because set of irrationals is uncountable in R. So this question is actually option D. So moving to the next question, here we have a problem where we are asked to find the number of cosets of a particular subgroup H in a group G. We are given both the groups are with operations matrix multiplication, and G is defined in this manner, where omega is specially taken from F, where F is nothing but set of all omega belongs to C, where omega raised to 2020 is equal to 1. That means set of all 2020th roots of unity. You know, if we solve this equation, you're going to get 2020 roots, and all those we call it as 2020th roots of unity. F is set of all 20 roots of unity, and we are asked to find number of causes of H in G. So what I'm going to use here is that I'm going to use the idea of cosets and first isomorphism theorem to get the answer for this question. So here we know that the quotient group G by H is defined if H is actually a normal subgroup of G, and the order of G by H gives you nothing but the number of causes of H in G. Moving on to the solution, we'll try to show first that H is a normal subgroup, and then we'll try to count the number of elements. So we define a mapping phi from G to C star such that phi of this element is actually omega. So whatever is coming here, matrix is coming here, set may be any complex number, whatever is coming in this position, that is omega, usually comes in this position as per our definition, because here G is defined in this manner. So that element is actually basically mapped to omega, which is actually a complex number in C star. So clearly you can see it's actually it's an homomorphism, because if you multiply phi of A star B, you get phi of this matrix, and this will be mapped onto omega 1 omega 2, which is nothing but equal to phi of this matrix into phi of this matrix. So what we're getting is actually an homomorphism from G to C star. So now and we'll go to find the kernel of homomorphism so that we can use the first isomorphism theorem. So the kernel of this homomorphism is basically a matrix containing elements 1, 0, 1, where Z is actually an sorry, it's not Z, this is not Z, it's actually a complex number, set of complex numbers. So here if you see, you're going to get the kernel. Kernel means set of all elements which are mapped onto the identity in this group. So in C star the identity is 1, right? It is also an element in F, because 1 power to 2020 is actually 1, so it's also a root of this particular polynomial. So what you get here is the elements which are mapped onto 1 here should be basically, there is this omega is 1, so basically it should have something like here you should have 1, right? Set of elements of this form will only be mapped to 1 here. That means your kernel contains elements of this form, that is matrices, 2 by 2 matrices, where this Z can be any complex number. So what you get is this, we got this set as actually a kernel of this homomorphism. So we know that it will be a normal subgroup, so H, and in fact this set what we got is nothing but the H what was given to us. This was the H given to us, so we got H is actually a normal subgroup of G now. So if H is a normal subgroup of G, we can define G by H, that is the quotient group G by H, and the order of G by H will give you actually the number of causes of H in G. So by first isomorphism theorem, what we get is nothing but G by H will be isomorphic to phi of G, and we can just count what are the elements you're going to get in phi of G. So the elements you're going to get mapped, for example, if you take 1 here, omega, if you take omega here as 1, it's actually a root of that particular polynomial, omega raised to 2020 minus 1 equal to 0. So if you give 1 here, it will be mapped to, that is 1, Z0 1 will be mapped to 1, and Z can be any number, right? So if I take Z as 1 plus I, or if I take Z as 2, all those elements will be mapped to 1, right? So the image, so that means all those elements in this domain will be mapped to this 1 here. Next set of elements, the second root if you take, suppose is omega, then what you have, you just vary all the Z's here, you get another set of elements, another set of matrices which all be mapped to omega, right? So basically we are going to have phi of G is nothing but set of all omegas where omega raised to 2020 is 1. That means you get all the 2020 roots of this equation, that is omega raised to 2020 equal to 1 as the images. So since we have 2020 roots, what we are going to have is phi of G, cardinality of phi of G is to be 2020, and hence the number of elements in G by H is also 2020. So we get the cardinality or the number of causes of H in G as 2020. So the correct option is C, that is 2020. See, when you take here you can see F is set of all omega belongs to C such that omega raised to 2020 is 1. The polynomial what we have is omega raised to 2020 minus 1 equal to 0. So this polynomial will actually have 2020 roots itself, not at most 2020 roots. If it is say R set of real numbers you are going to take, then you can say it has at most 2020 roots, but in complex numbers we'll be able to attain all the roots, so we'll get all the roots of that particular polynomial. That's why I have taken exactly 2020. Hello guys, let's see the next problem. That is, we are given G is a group with identity E, and H is an abelian non-trivial proper subgroup of G with some property, and for all G not in H, and if K is equal to G belongs to G such that GS is equal to HG for all H in H, then we are given 4 options. We have to check which of the following options are correct. So one thing you can see here is that if you look at this K, it is containing set of all G in the whole group G, for which for all H in H, GH is equal to HG. That means we are actually given nothing but the the centralizer of the group H in G. So K is nothing but centralizer of H in G. You can see here H is actually an abelian group, abelian non-trivial proper subgroup of G with the property that H intersection G inverse is equal to E for all G not in H. So for all G which not in H, this is true. Okay, that has to be made a point in your mind, as a point in your mind. So what is I think for this particular problem is that this argument is true, because if I prove this argument, I can show these two are wrong, or even my proof actually will give you like how I show these are wrong. So the first argument what I have is that H is basically a subset of K, because if you take the elements in, because K is set of all G in whole group G for which all H in H, GH is equal to Hg, right? So if you take G to be an element of H, which is also inside G, right? If you take G to be an element of H, and since H is abelian, GH will be equal to Hg for all H in G, right? So K will contain extra elements also in G, but it will contain all the elements in H. That means if you take any element in H, it will be inside K. So we can say that means if you take X belongs to H, you can show that X belongs to K. So you can say H is actually a subset of K. So next what I'm going to prove is that K is also a subset of H. Okay, so next I'm going to show that K is actually in fact a subset of H. How I will show that? I'm going to do proof by contradiction. Suppose I assume that K is not a subset of H, so therefore that means K is not inside H. So K is not a subset of H. Therefore there exists an X in K such that X is not in H. Clear? Because if K is not a subset of H, definitely there is at least one X in K which is not in H. So for that particular X, we have that because X is in K, so that by this definition of K, XH will be equal to HX for all H in H. Or what we get is nothing but XH is equal to HX, or we get XH inverse is equal to H, or if you take the intersection, you're going to get again H itself, because both are same. But then what we have is actually a contradiction. So why we get a contradiction here is because here you can see any X or any G which is not in H, it should satisfy this particular condition, right? So here, but we have got an X which is not in H, is actually outside H, and because X is in K and K is in G, and for that particular X we got X inverse intersection H to be H, not singleton E. So that means we have a contradiction. So that means K has to be a subset of H. So hence we get K is equal to H. So this statement is true. So similar argument. So if when this C is true, we can say that A and B are false. Now the next argument what we can make is about the option D, also in the same or similar manner. So the option says there exists no abelian subgroup L subset of G such that K is a proper subgroup of L. So let us assume that there exists such an abelian subgroup L of G such that K is a proper subgroup of L. So we are assuming that such a group exists. So if you take an element in L minus K, it means if you take an element in L minus K, we have this property that the C is true. So what we can say is that the element, so any element on X, any element X in L minus K, we have the property that X intersection X inverse is equal to E. This is actually singleton E by this property of H, what is given to us, right? So because K is H itself, right? So we have this property. So there exists at least one element Y in H, right? there exists at least one element y in H, such that we are getting xy is not equal to yx. Yeah, it's not x actually, it's actually H. Intersection x H x inverse should be E. So in this case, what we are getting is we have at least one element will exist of this kind. So we can say that L is not abelian, and thus we can conclude that option D is false. Okay, so the next problem we have is let phi be a mapping from S3 to S1, the circle group under multiplication of complex numbers, what we have seen just in the last problem. We are given let phi from S3 to S1 be a non-trivial non-injective group homomorphism, and the number of elements in the kernel of phi is what? That is a question. So here also we can use the idea of first isomorphism theorem. You know, the identity in S1 is nothing but the number, complex number 1, right, for which the modulus is 1. So what I'm trying to do here is I'm trying to find all the kernels possible for an homomorphism which I can define from S3 to S1, and if I could find the kernel, then I can say it will be nothing but a normal subgroup of S3, right? So we have a homomorphism from S3 to S1, kernel of that particular phi is actually a normal subgroup. So what I can say is we have three possibilities basically, that is it could be singleton E in S3, or it could be something like A3, subgroup A3, or it could be the whole group itself. So these are the only possibilities we can have as a normal subgroup of this particular group S3. So if I take the kernel of my mapping to be identity, if I take a mapping in such a way so that kernel is actually singleton E, then the mapping will become an isomorphism, but we don't want the mapping to be an 1-1 here. You can see it's non-injective group homomorphism. That means we cannot choose a mapping for which the kernel is identity, singleton E. But if I choose a mapping for which the kernel is A3, then I will get definitely a non-trivial non-injective group homomorphism there. So that is not an issue. And suppose if I am going to choose the whole group itself, what I am going to get is that the kernel, like the kernel, if I am going to choose a mapping which the kernel is the whole group, that means whole group elements are mapping to the identity in S1, then what you have is actually a trivial map. So, but we need a non-trivial non-injective group homomorphism. So the only possible answer or only possible group which has to be the kernel of your mapping is A3. The normal subgroup is A3. So the number of elements in A3 is nothing but 3 factorial by 2, that is 3. So the answer to that question is actually 3. Now we'll move to the last problem. This problem is also an interesting problem. We're given a group of ordered 57 which is not cyclic, and if G contains a unique subgroup H of order 19, then we are asked to find the order of element G which is not in H. So here you can see 57 is actually not a cyclic subgroup. The order of the group G is not actually a cyclic group with order 57. That means that there is no element of order 57 in that particular group, because if it is cyclic, obviously you are going to have one element of order 57 in that particular group. So since the group is not cyclic, we can say that none of the elements in that particular group has order 57. That is the first implication you must derive. So the order of the elements, other elements possibly are nothing but 1, 3 and 19, right? Because you know order of the elements in a group will divide the order of the group. So the possibilities are 1, 3 and 19 only, right? And 19 times 3 times 1 is 57, you know that. So next observation is that the number of elements of order 19 are going to be in H, right? So the elements and the number of elements of order 19 are going to be 5 of 19, that is 18. In fact, these are the only elements of order 19 in G. And and also obviously it is the Euler torsion function, that is phi of 19 is a prime number, so you get exactly phi of p to be p minus 1. So we have total 18 elements plus an identity element in that group, and identity element obviously has the order as 1, and all other elements in that H has order 18. And this is a unique subgroup of order 19 in that particular group G having order 57. So what we can say here is that if you take any element which is not in H, so elements which don't have order 19 and elements which is not having order 1, that is because identity elements also belong to H, its order is 1. So if you take an LG which is not in H, then we are excluding all the elements with order 19 and order 1, and you're going to get for all of the elements order of G is going to be 3, because all the elements will basically have order as 3. So the answer to the question is actually 3. See, here I told that all the elements here have order 19 and phi of 19 is equal to 18. You know that order 19 is actually a prime number, and so every prime order group is actually cyclic. Result in cyclic groups that if D is a divisor of the order of the group, number of elements of order D is basically phi of D. That is, in this case we get answer as phi of 19, which is equal to 18. So that is why we got actually the number of elements in the group as 18 elements with order 19, and one element, that is identity element, which is order 1. Thank you for watching this video, and please subscribe this channel for getting more updates and more problems of this kind. Thank you.